Howdy calculates. So today we're going to look at inverse functions, except we have a typo in your notes. So I'm going to assume that your notes look like mine. This should say f of x equals x plus 3. Alright, so now based off of how f of x is defined, if I have a domain of the numbers 1, 2, 3, and 4 and I plug them in, then I'll get the ordered pairs 1, 4 and 2, 5 and 3, 6 and 4, 7. Not really any magic to that. And so remember, a function takes the domain values and maps them onto the range values or the y values. And so from this, of course, I know my domain are the numbers 1 through 4. Those, of course, are my x values. And my range is 4, 5, 6, and 7. Those are my y values. And remember, in order to be a function, each x has a unique y so that it will pass vertical line test. Now, if I interchange the domain and range, then I'll get the inverse. And the notation, of course, is with the power of -1. That's read f inverse. And so then the set looks like 4, 1, 5, 2, 6, 3, and 7, 4. So graphically, I don't know if you remember this at all, but they are a reflection across the line y equals x. And if you graph them, you'll convince yourself of that. And so now, by definition, a function g is the inverse if and only if, so this should be 3 f's, because that's how I say if and only if. We'll write that there once just so you remember what it says. So a function g is an inverse if and only if when I change the order of the composition and I do the composition in either order, both of them result in x. In other words, I can think of it as g undoes f, and at the same time f undoes g, so that I end up with whatever I had inside. And that's what makes them inverses of each other. And if g is the inverse of f, then f is the inverse of g. And the domain of g is the range of f, and the range of g is the domain of f. And so as you can see up above, their domains and ranges, if I went back and listed them. So let's say g is equal to f inverse, then the domain of g we could see is 4, 5, 6, and 7, which was the range of g is 1, 2, 3, and 4, which was the domain of f. And so, of course, not every function will have an inverse, because not every function can be a reflection across y equals x. But if it does, it is unique. In other words, you only get one reflection. which would make sense. Think of it as you only have one reflection. And then, of course, for a function to be one-to-one, it now has to pass horizontal line test. So if it's a function, it passes vertical line test. If it's a one-to-one function, it'll pass horizontal line test as well. That way, each x has a unique y, and each y has a unique x. So, new vocab. Strictly monotonic is a function that's either strictly increasing, meaning that my y values, or my slope rather, is positive, or it's strictly decreasing, meaning my slope is negative on the entire domain. And you can think of graphs that are like that, where the slope is all positive. Of course, I could have a line doing that. In the same way, the slope is all negative, I could have a line doing that. Those would be either strictly monotonic. Those would both be strictly monotonic. Okay, and then last but not least, so a lot of vocab, a lot of definitions coming at you. A function has an inverse if it's one-to-one. And if f is strictly monotonic, I need to add a little on its domain. Then it's one-to-one, and therefore it has an inverse. And you might see that in multiple choice on a live test. So to prove a function has an inverse, I can prove that's monotonic, which would be easy by showing what the slope is. So if I find f prime and it's always positive or it's always negative, I've shown that it's monotonic, and therefore I know if, again, it's strictly monotonic, then it's one-to-one and has an inverse. Now, it's often easier to prove that an inverse exists than it is to find it. For example, if I had this function x cubed plus x minus 1, remember, in order to find an inverse, I would switch the x and y and then solve for y. But it's going to be difficult to isolate y when I have a cubic. However, it's not that difficult to find the slope on this and to prove that that's positive all the time, because it doesn't matter what I plug in for x, it's going to get squared, and then I'll multiply by 3 and then add 1. So this is always positive. And so therefore I know, hey, if the slope is positive everywhere, then this is strictly monotonic. And if it's strictly monotonic, then it has an inverse. Even though I can't necessarily find it, or at least definitely not easily, so therefore has inverse. And you probably wouldn't actually be asked to find it, you would get asked if it has an inverse. And so rather than trying to find it, that's what I could do. So some rules about continuity and differentiability of inverses. If f is continuous, then the inverse is continuous. If f is increasing on its domain, then f inverse is increasing on its domain. If f is decreasing on its domain, guess what? So is f inverse. And if f is differentiable at c, where the slope is not equal to 0, then copycat, f inverse is also differentiable at c. And remember, the slopes of a function and its inverse are reciprocals. And again, that goes back to the fact that they are mirror images across y equals x. All right, so we're going to test this. So first of all, I have the function f of x equals x squared. So remember, if I'm going to find the inverse, I have to switch the x and y. So instead of y equals x squared, I'd have x equals y squared. And then when I solve for y, I get y equals, the square root of x. And in order to make sure that it is a function, I have to make sure that I only take the top half, because this is in fact a sideways parabola. And so I can only keep the positive square root. All right, so now over here on the left side, I want to find the slope at x equals 2. So of course I have to first figure out the generic slope, which taking my first derivative is 2x. And so the slope at 2 is 4. And so now I'm going to convince myself that they are reciprocals on the other side. So if I take the derivative, I'll get 1/2 x to the negative 1/2. So over on the original function side, f of 2 is 4, which means over here, so I have the point 2, 4. So over here, and that's the slope for it. So over here I have the point 4, 2. Because remember, for an inverse, they switch. So now I'm finding the slope at this point. So now y prime, the slope, would be 1 over 2 square root of 4. Remember, I have to plug in the x value. And I'll get 1 over 2 times 2, which is 1/4. And oh, by golly, those two slopes are reciprocals of each other. So at the mirror points, so 2, 4 and 4, 2, their slopes are reciprocals. That's an important point. You're definitely going to see that question on the AP test. So now in this next problem, if I want to prove that they are inverses algebraically, remember I have to check f of g of x and g of f of x and make sure that both of them end up giving me x. So I'll start with f of g of x first, which means I'd be doing f of 1 minus x over x. But remember, f of anything, if I said f of 7, you'd plug in 7. If I said f of negative 22, you'd plug in f of negative 22. So I want f of 1 minus x over x. So I'm going to have 1 over 1 plus, and now I'm substituting this stuff in, 1 minus x over x. Oh my goodness, this is going to be a big, fat, scary mess. So let's see, a common denominator. This will be x over x plus 1 minus x over x. And so on bottom, I have x plus 1 minus x all over x. So now I have 1 over x, multiply top and bottom by x,